to February. You know, today is Opera Day, and I thought, in the spirit of the day, I would sing a few bars from my favorite opera, Turandot by Puccini. So let me back up to my microphone a little bit so I don't redline anything.
Mike, I think there's something wrong with your audio. Mike?
You didn't hear me?
No, couldn't hear you.
Well, I would sing more, but we really need to get on with this webinar. We're starting late, so maybe some other time. What are we talking about today? Well, we're going to explore how to create energy efficient, low emissions, all electric homes that meet our electrification challenges. And we're joined today by building science consultant, Steve Easley. Now, if you haven't seen or heard from him before, well, that's odd, because he's an internationally recognized building science expert and educator. He has more than 30 years of industry experience performing thousands of job site quality surveys and presenting building science seminars, just like this, around the world. His work focuses on increasing quality of construction, sustainability, and performance while reducing costly mistakes that lead to construction defects and callbacks. Steve's mission is helping industry professionals build and remodel structures that are durable, energy efficient, healthy, and comfortable to live and work in. Now, we have a great sponsor for this webinar, and that's PowerShift by NV Energy. They have a program that helps residential and business customers conserve energy and save money on their power bills. PowerShift is a one-stop resource to find energy-efficient products and services. For more information, please visit their website at nvenergy.com/PowerShift. Now, during the course of today's presentation, you can submit questions for our guest. Simply use that questions box on the right side of your screen. We're going to take those questions during Steve's presentation. All right. Aloha, Steve.
Aloha. Nice to be here. Thank you for the introduction, and welcome everybody. So today's class is really just about understanding, what we could do to, reduce our carbon emissions and understand the kind of the cost-effective concepts of electrifying our homes. It's a little bit of a complicated process in the sense that, depending upon where you're at in the country, your grid may or may not be, more friendly towards this whole concept of electrification. But certainly electrification is key to, reducing the impacts of climate change. So in this class, we're going to focus on mostly the technologies and concepts and best building practices that will give us the best pathway for electrification of homes. I would like to point out that one of the issues associated with doing a national webinar like this is that codes vary widely. Building practices vary widely throughout the United States. So please keep in mind to always check your local construction practices, your local building codes, all those types of things that really have an impact on what you're allowed to do and kind of what you're not allowed to do. One of the things that I think it's important to recognize that if electrification is really going to happen in the United States in kind of a meaningful kind of way, it's going to happen on the customer side of the meter. I'll give you a great example of that. I'm building a house in Scottsdale, Arizona, and when I submitted my plans, they basically said that I had to upgrade my service interest because I was switching from my natural gas furnace and natural gas water heating, my natural gas furnace, natural gas cooking, all that was switching to electric, plus we have an electric car. So they said, well, we're not really sure that, your transformer is going to be able to handle that. And so they did some analysis and said that I might have to actually pay upwards of $10,000, $12,000 to replace the transformer. So it depends on where you're at in the country. Some utilities may or may not, be more open to providing, this pathway to electrification. And it's not that my particular utility was not. It's just the way that the structures or these utilities are set up. So my point in all this is that for electrification to happen in kind of a meaningful way, it's probably going to have to happen on the customer side of the meter. What I mean by that is that as we start to switch to all electric everything, the loads are great. And the local infrastructure might not be able to quite handle that well. So we can help that by making sure that we have a really good building envelope, making sure that we're using, friendly equipment in terms of amp draw and those types of things. Those are the kind of things I'm going to get into today. So we want to identify the 5 key technologies that provide the most cost-effective pathway for electrifying homes, identify how variable speed heat pumps are very, very different in terms of efficiency, comfort, and operation. We certainly now have cold climate heat pumps that have really changed the game. The heat pumps that we had of yesteryear are certainly not like the heat pumps of today. I remember one of the first homes I built back in the late 1970s was that we had a heat pump, and once the temperature got below about 35 degrees, it would still work, but it wasn't very efficient. And today's heat pumps are way, way different, and I'm going to explain why. We're going to identify the top 10 building efficiency measures, methods, and technologies so that we can reduce our electrical demand. And that's what I mean by being able to, work on the on the customer side of the meter. In other words, if we can reduce the loads, that certainly reduce the stress on the grid and reduce the potential for having to do things like replace transformers, things like that, because maybe your localized grid isn't capable of handling, several homes with all electric everything. We're going to identify the top 10 design and installation mistakes that lead to poor heat pump performance and space conditioning, water heating, and leading customer dissatisfaction and rejection of these types of technologies. Once these technologies are designed and installed properly, they work very well, as you'll see from some of my real world examples today. So, I can show you, we're going to show you some examples of heat pump technologies that work well below zero for those of you in the cold climates. So again, as Mike said, it's a pretty informal presentation. We got a lot to cover today, but we're going to try our best to get through that and then also answer your questions. I'm a big believer that if you have questions, don't forget to raise your hand and ask questions. I'm happy to try to help the best of my ability. Okay. A couple of resources you might want to think of. If this is, we wrote a book for the California Energy Commission called Real World Zero Net Energy, and you can download this book for free. I'll tell you how to get that. If you go on Amazon, you can buy it for $30. I don't encourage you to do that at all. It's paperback, but you can download it off my website for free. And this is a book, again, we did for the California Energy Commission that sort of documents a series of zero net energy homes that we did with Habitat for Humanity out in the Central Valley of California. So you simply go to steveeasley.com, and that's E-A-S-L-E-Y. Just Google Steve Easley. It typically take you right to my website. And I don't ask for your personal information or anything like that, so you don't ever have to worry about being on some mailing list. But anyway, if you go to articles and publications page of my website and then click on Steve's articles and books, you can download these books and publications there on a variety of topics that relate to this. Also, if you go to Green Builder Magazine and you click on Vision House and then you click on the Scottsdale Revision House home, you can see kind of what we're doing with this project that I'm building in Scottsdale, Arizona, for the home I'm building for ourselves. I think it's important to recognize that almost all major scientists, over 90%, in fact, of scientists in the country agree that climate change is real, and we're looking at 5 different organizations that track climate issues, and they're all pretty much spot on with regards to what's happening with being in agreement with how much the Earth is warmed. And it's about 4 to 7 degrees centigrade over the last 5,000 years. Now, get this, in the past 100 years, it's raised almost 3/4 of a degree. So that's what's got people alarmed, is the rate of change. And we go through, in the United States, about 40 trillion gallons of oil burned since 1980. That's give you an idea how much that is. That's never covered the state of California, about 16 inches deep in oil. About 96 million barrels of oil per day, 19 in the US, about 30 trillion cubic feet of natural gas per year, if you can believe that. And for every kilowatt hour of electricity used, that's about a pound of greenhouse gases that goes in the atmosphere. And so as far as natural gas goes, that's about 120 trillion cubic feet worldwide. We had about 50 billion tons of carbon each year, and it takes about 1,000 years for nature to remove it. So there's no doubt that as population has increased in the last 100 years, that we have really increased our carbon footprint, and certainly that has had an impact on climate change, and that's reflected itself into many natural disasters. Like, for example, just in 2022, just last year, we had over $165 billion in damages due to weather-related disasters. And then when you look in 2021, we had over $20 billion climate-related disasters. And then worldwide, check this out, we had over $47 billion plus disasters, some of which as high as 75 billion. And so there's no doubt that we're starting to see the impacts of climate change. And so that's why electrification is really such an important issue, because as we start to move away from fossil fuels, for natural gas, for example, for heating our homes and heating our water on a localized level, that really helps us offset that with renewable energy. So that's kind of the concept behind electrification, is really just trying to move away from using fossil fuels on a localized basis. So that means not only just natural gas appliances, but also electric cars and so forth as well. That's certainly transportation is a huge impact on climate change as well. And then when you look at what's happened since 1980, and you look at these billion-dollar weather-related disasters, you can see it's pretty plain to see that as we've added more carbon to the atmosphere, we have more natural disasters. So with that in mind, that's really why moving to electrification strategies is really important. So about 83% of all new homes have gas furnaces, about 12% were heat pumps, about 57% of existing homes are now gas, and about 10% of existing homes are oil or propane. So it's not just natural gas, it's oil and propane and some of these other fuels as well. And so in fact, with all electric home would save about 2.5 metric tons of carbon each year per house. In the United States, we have roughly 100 million homes, and roughly. Okay, so top 5 solutions that I think we need to pay close attention to is to switch to variable speed heat pumps for space conditioning and water heating. Notice I said variable speed, because there are a big difference between your typical single speed and 2-speed equipment in terms of not only their overall efficiency, but also their amp draw, which has a huge impact on the grid. Also switching to induction cooking, switching to heat pumps for clothes dryers. And also, maybe I didn't say this, but I meant to say not just heat pumps for space conditioning, but also water heating. And then also employ a real-time IAQ sensors so that we can control our ERVs. Traditionally, we run our ventilation systems according to ASHRAE 62.2, which is a standard which says you have to, based on the square footage of your house or however many people you living there, that you're providing real-time ventilation. Using real-time IAQ sensors that can actually monitor indoor air quality and control those ERVs based on your true indoor air quality is definitely a step in the right direction, instead of a formula that just runs the fan so many minutes out of every hour or so many hours out of every day. And then, of course, I can't emphasize the importance of making the closure, your building enclosure, more energy efficient. That's really, really critical. A good example of that, I was talking to a person yesterday that said they put in a heat pump in the Northeast, and they said they couldn't get their house over 63 degrees, and that's just not necessary. I mean, I'll show you examples of how these heat pumps can work really well. So having your building envelope in shape before you do some of these measures is really, really important. So the bottom line is, why heat pumps for heating and cooling and domestic hot water heating? One, they're 2 to 4 times the efficiency. They have lower operating costs. They can have lower operating costs depending upon your local utility rates. They're certainly better suited for low load homes. As we make our homes more energy efficient, we tend to have equipment that tends to be kind of oversized. And the beauty of variable speed heat pumps is that you're not quite so worried about them being oversized, because what they do is they know the temperature of your house, that you set what you want your temperature of your house to be. They know the outdoor temperature. They know what the ramp up time would be to make this happen, and so it can actually vary the speed of the compressor to your actual load. So you're not really worried quite so much about oversizing of this equipment. You certainly can have greater comfort because you don't have these big temperature swings. They're compact in size to make it easy for zoning. I'm going to show you some real world examples of that, because you could use these individual evap coils to have individual zones so that you can create individual temperatures for each room based on your needs. You don't have the venting issues that you have with combustion appliances that you typically see with water heating and furnaces. And then we have less environmental impact than you have with other types of systems. So those are kind of the top big reasons why it makes sense to do this. When you look at your traditional furnace equipment, basically what you have is some type of a burner and a heat exchanger, and the newer systems have much more sophisticated heat exchangers. This here is a furnace that would be about 65% efficient, wouldn't even be allowed by code for that matter. But newer systems are anywhere between 80 and 98% efficient on the gas side, but still you're putting a lot of carbon in the air on a localized basis. Whereas when you're dealing with your traditional heat pump type systems, you typically have, if it's a split system, you typically have an indoor unit, and that indoor unit has a inside coil. It has a return air duct, a supply air duct, a blower that distributes air throughout the home. And then we have a line set that connects to the outside unit. And that's basically the components that we see in your traditional heat pump designs. And so the new technology is not much different, except it has a variety of different configurations. So with that in mind, when we tend to look at the older equipment, we're looking at, we have basically two-speed, single-speed equipment. The newer technologies, we've had variable speed equipment out there for some time, but when we're looking at the newer technologies, we typically are using inverter-based compressors, which means that they can really vary their speed based on the load. So very unique type of systems that are available, and they're very much more energy efficient. Okay, so how is a heat pump more efficient? How does a heat pump basically create heat out of the air? Well, the air has quite a bit of heat in it. In fact, some physicists estimate that air at 0 degrees has 80% or more of the heat of air at almost 100 degrees. So the interesting thing about this is there's already quite a bit of heat from the environment. So what a heat pump does essentially is, let's just say we have heat in the air, and even if it's 30 degrees outside, or for that matter, even if it's 5 degrees outside, as you'll see in a moment from some of my diagrams, there's still quite a bit of heat in the air. And all we do is take our heat pump, basically takes like 1 unit of electrical power from the grid, and then uses that through the refrigeration cycle to extract that heat out of the environment. So we get 3 kilowatts of energy from the air heat that's already in the air, and then we get 1 kilowatt from the grid, and that produces for example, kilowatts of heat going into our homes. And so if we had no heat in the air, absolute zero would be like 459 degrees below zero. So there is quite a bit of heat in the air, as I said, and all a heat pump does is use the magic of refrigeration to extract that heat out of the air. So let me show you an example of this, and then I'll ask for some questions. Here's what I have here is a thermometer, and you notice it's at 70 degrees. And then I'm going to take some alcohol here, and I'm going to pour it over the probe of this. And what I want you to notice is how quickly the temperature drops as a result of evaporation. So that will be cooling via evaporation. So as I pour the alcohol over the probe, you'll notice that the temperature drops very, very quickly. And so essentially, on one level, that's kind of how an air conditioner works, except we use refrigerants that have the capability to boil at much, much colder temperatures than, say, alcohol, which is, I don't know, probably 70 some degrees, I would guess, to 80 degrees. But notice here how our temperature drops to 56 degrees from 70 degrees. So it's like a 14-degree temperature drop pretty quickly. All right, so how does that work? When we think about the modern day refrigeration cycle, I think people are always kind of confused about that, kind of like, how does this possibly work? How do you take heat out of the air and move it into our house? Well, I think the easiest way to look at it is like a refrigerator. Your refrigerator in your home, it takes heat out of your freezer, it takes heat out of your icebox portion of it, or the refrigerator portion, and it takes that heat and just dumps it in the air in your house. And so it uses that cooling, that refrigeration process to make this happen. So let's first talk about the cooling cycle. And this was first developed by Willis Carrier back in the early 1900s. He was actually trying to figure out a way to dehumidify the air for a printing company that was having problems during the hot, humid weather with their printing presses jamming up. And so he figured out a way to reduce the humidity in the air. And in the process, process kind of developed the modern refrigeration process. So when we talk about the refrigeration cycle, whether it be a heat pump cycle or a cooling cycle, it's basically the same. The only difference is we just reverse the cycle. So we start with, in this case, a refrigerant, and which boils at minus 55 degrees, okay? And so let's just look at some of these temperatures and pressures here. And we have a compressor, and we have an outdoor coil, and we have an indoor coil. And so let's just say we start out with a high pressure liquid, just like my alcohol, my last little video. And let's just say for fun, it's at 100 degrees and 319 pounds per square inch. Then it goes through an expansion valve. And when that liquid changes from a liquid to a gas, just like in my little video a minute ago, we notice cooling happen. So anytime I change something from a liquid to a gas, I have to add heat or take heat away. So what happens is as that refrigerant goes through this expansion valve into the evaporative coil, it starts to change from a liquid to a gas, and it absorbs heat. So we have room air for our blower motor and our furnace or air conditioner that is pushing air across that coil. And so the room air, that heat always goes from warmer to colder. So it's absorbed into that refrigerant, and the outdoor air is 55 degrees. Our pressure drops to 143. Our temperature drops to 50. It goes through the compressor. The compressor compresses it again until it's just about ready to condense. And then it releases that heat into the outdoor air. So that's how it works during the cooling cycle. We simply are taking this concept of boiling and compressing the liquid to really just move heat from one place to another. So heat pumps don't create heat. Air conditioners don't create cool, essentially. They basically just move that heat from one place to another. And so when we talk about a heat pump, all we do is add a reversing valve. And in this reversing valve, what that does is that reverses the cycle. So now we're taking heat out of the outdoor air and we're moving it to the inside of the house. And so that's simply how a heat pump works. It's a pretty simple, reliable process. And in today's units, they've certainly made tremendous strides in their efficiency and performance. So Mike, do we have any questions so far?
Yeah, actually, Steve, I was just going to interject with one or two. So we do have a question from Gene wanting to know if a properly sized heat pump will allow an 8-degree night setback in older homes.
Yeah, my opinion about that is highly unlikely. And the reason for that is, in fact, most of the manufacturers are leaning more towards advising people not to do setbacks. My guess would be about the best you could ever do is maybe a 2 or 3 degree setback. My gut feeling about that is that in older homes, because of the fact the heat pumps, their capacity is a function of the outdoor air temperature. Certainly their efficiency is a function of the outdoor air temperature, and the recovery time is in fact is related very closely to the outdoor air temperature. So what happens is if you've got an older home, and I'm going to get into this and talk about the building enclosure stuff here very quickly. But if you have an older home that is not very efficient, it leaks like a sieve, it's not very well insulated, when you set back that temperature, that unit has to work so much harder to extract that heat out of that colder outdoor air that you're probably not going to be able to set back your thermostat. So most manufacturers are not encouraging setbacks. Just set it and forget it at the temperature that you like. So that would be my thought on that, Mike.
All right, sounds easy enough. And then one other question from Robert. He wanted to know if at some point you're going to get into ground source heat pumps and talk about maybe advantages or disadvantages of those. Didn't know if that was part of this or not.
Yeah, I am briefly. I'm going to talk about that. Absolutely. Yeah, there's no doubt about it that ground source or water source heat pumps. Obviously, you're using the heat that's stored in the ground or the heat that's already stored in the water, and so you don't. They're much more efficient. A little bit more expensive, but they're definitely much more efficient. So I will talk about that. So with
Okay,
regards
great.
to the way we measure the efficiency of these equipment, gas equipment, we measure through annual fuel utilization efficiency. Air conditioners, we measure that through seasonal energy efficiency ratio. And sometimes we use EER. For those of you out in the West and the Southwest in particular, where you have very hot temperatures, EER is a much better, or EER2 is a much better metric to measure the overall performance of your air conditioner, for example. Coefficient of performance is another way that we measure that, and I'll talk about that. And then heating seasonal performance factor and heating seasonal performance factor 2, as a result of January 1, that we've had some significant changes. So the heating seasonal performance factor is a big metric that we use to measure the performance of heat pumps, and it's simply the total heating season BTU per output divided by the electrical power input in watt hours. And then as of January of this year, we now have what we call heating seasonal performance factor 2. Okay. And then when you talk about COP, a lot of people like to use this coefficient of performance. What does that mean? It simply means that COP of 3 means that 1 kilowatt hour of electricity yields 3 kilowatt hours of heat. Now, it's not uncommon to see some of the newer heat pumps be up in the 4 range. So that means, you get 1 kilowatt hour of electricity yields 4 kilowatts of heat. And again, we're not creating or generating heat. We're just simply moving that heat from indoors to outdoors. And as you can imagine, as the outdoor temperature gets colder, it becomes a little bit more of a struggle. The unit has to work harder to do that. But these new cold climate heat pumps do a much better job of doing that. So the outdoor air, as I said earlier, already contains heat, and heat pumps simply extract that heat that's already in the outdoor air and move it to the indoors. So again, the coefficient of performance, if you're interested in this later, you can review this presentation because it's going to be recorded. It's basically the useful energy output in BTUs per hour divided by the input in watts times 3.413 BTUs per watt, if you're interested in those technical details. So when we talk about SEER or SEER2, that's typically what we're referring to for air conditioning efficiencies. So EER is simply the BTUs per hour divided by the input wattage, and SEER is that for the entire cooling season. Now, for those of you that are out in the Midwest and out east, SEER is probably, and SEER2 is probably the most important number if you remember when you're selecting an air conditioning system. But if you're out in the West, we care more about EER or EER2. So EER is simply the net capacity in BTUs divided by the power input. So it's real simple. So if I've got a 4-ton unit or a 48,000 BTU per hour system, and it takes 4,800 watts to operate that, it has an EER of 10. And so you may be asking, well, what is this SEER2 and this heating seasonal performance factor 2? Well, they changed as of January 1 of this year. Basically, there has been some concerns about the methodology of the old system for really determining what the heating seasonal performance factor and the SEER ratings were. They said it wasn't very realistic because it didn't really reflect real world performance, because the static pressures, when you look at the pressure buildup that your typical ductwork provides, they're looking at, in the real world, you're probably looking at more like 0.5, whereas when the old standards were like 0.1. So they all got together and said, you know what, we need to make this system for testing these units for SEER and for heating seasonal performance factor a little bit more realistic based on how people's systems are actually installed in their homes. And so they said, we're going to revise all that. So they came up with this heating seasonal performance factor 2 for heat pumps, and then also SEER2 for air conditioners. And so basically, depending upon where you're at in the United States, whether you're in the north or the southeast or the southwest, whether you have a split system, which is a separate outdoor and indoor coil, or whether you have a package system where it's all in one package, that determines really what those ratings are. So you can check based on where you're at, and it's pretty easy because the manufacturers, they just can't sell equipment anymore that doesn't meet the new DOE standards. So I don't think you have to worry about buying a piece of equipment that doesn't meet the standards unless somebody is using really old equipment. Questions, Mike?
Hold on a second. We have one question here. Chet wanted to know, can you estimate the temperature of heat pump heated air at the outlet versus gas hot air heat?
Hold on, I'm going to show you some examples of that. I'm even going to show you one of my own examples from the heat pump that I have. So hold on, it's again, the discharge temperature is a function of the equipment efficiency and certainly the equipment capacity, but also the outdoor temperature to some extent. But that's changed with the cold climate heat pump. So it's kind of a complicated answer, but I'm going to get to that. Now, for those of you that might be viewing in from the West, when I talked earlier about why EER versus SEER, this is a good example. Let's just say we have a SEER 10, 12, and 14 piece of equipment. That's what we're looking at here. And 85 degrees will be SEER 10, 12, and 14. But look what happens as the outdoor temperature gets warmer. So what I'm saying is that the seasonal energy efficiency ratios, even 2, they're based on getting some latent cooling capacity out of dehumidifying the air like we have out in the Midwest and out east. But in the West, where it's so dry, we don't really get any additional cooling capacity from dehumidifying the air because the air is already so dry. So when you look at 105 to 115 degrees, look how all of the SEER 10, 12, and 14 come together. And so this is why in states like California, for example, Title 24, they require that manufacturers post their EER efficiency, so people will base their purchase decisions based on real performance, not on this concept of SEER, which really doesn't apply. It's a national rating, but it really doesn't apply too much to the Southwest where it's very hot and very dry. Okay. All right, so let's kind of review this quickly because I know I'm covering a lot of material quickly. Efficiency of a system is related to the outdoor air temperature. In other words, as the outdoor air temperature drops, because the heat pump is basically trying to extract heat out of the air. So it makes common sense that if you have if the air is colder, that unit has to work harder and longer to extract that heat out of the air. The capacity in terms of this ability to cool your whole entire, or excuse me, heat your whole entire home is also based on outdoor air temperature and to some degree altitude because of the density of the air. The colder the air is, the longer the unit has to run to extract that heat from the air. So the colder the air, basically the lower the COP for traditional equipment. And so that's why it's important that we have our ductwork insulated, our ductwork sealed, our building envelopes well insulated, our building envelope fairly airtight before we would want to retrofit a heat pump. Now, it's also important to recognize that a lot of the systems require that you have backup strip heating in the older traditional heat pumps. That's because for 2 reasons. One, you just needed it to be able to heat your house because the older technology heat pumps, you know, they just didn't have that good of a capacity to extract that heat out of the air. And so once you got down into the 20s, or in some cases even higher than that, it didn't cost you any more to run these electric resistance strip heats than it did to run your heat pump because it was just had to work so hard to extract that heat out of the air. They just weren't that efficient. The newer technologies, they can get by without this backup heat. Now, that doesn't mean you don't need some type of emergency heat because, you know, if the system ever would go down and you're in a very cold climate, you want to have some type of backup heating. Now, another thing that's important to recognize is that the capacity is a function of outdoor air temperature. So if you look at a traditional single or 2-speed heat pumps, let's just say we start out here at 50 degrees, you know, we might have, you know, 100% of the capacity of our system. So let's just say we had a 4-ton system and it'd be operating at 4 tons at 50 degrees. But look how quickly the curve drops off as the outdoor temperature approaches 0. So we might have 22% of our capacity at 0 degrees, whereas at 50 degrees, we had 100% of our capacity. That's not the case for inverter-driven heat pumps. And that's one of the biggest misconceptions that we have out in the industry right now is people think that the heat pumps cannot heat your home in cold climates. And I'm going to show you some examples where that's true. Now, another thing that's important to recognize is that what happens to the discharge temperature at the registers. So for example, if I look at this chart here, this is the heat pump return supply air temperatures, and we look at this and we're looking at, just look at the supply temperatures here, where we're at 55 degrees outside, we might have a discharge temperature at that register of 125 degrees. But notice as the temperature starts to drop outdoors, then also the temperature at the discharge drops. So one of the things that I think I've noticed in these communities where they've basically outlawed new natural gas hookups, and people have replaced, and this, pay close attention to this, people have replaced their gas furnaces with heat pumps, and then they install these newer, they install the new heat pump, and the people say, wait a minute, it feels like cold air is coming out of the register. And the reason it feels that way is because heat pumps traditionally have a little bit lower discharge temperatures, your traditional equipment. Newer models, of course, can have much higher discharge temperatures. But my point is that if you don't insulate your ductwork and you don't seal your ductwork, and you can have lower discharge temperatures. And if you have air coming out of that register that's lower than your body temperature, it still might be 95 degrees, but which is plenty enough to heat your house. But if you feel that air coming off the register, you might feel it, since it's cooler than your body temperature, you might say, well, wow, this seems like it's kind of cool to me, and it doesn't feel quite right. So it's really important to help set customer expectations that their discharge temperatures out of a heat pump might be cooler than what they're traditionally used to. I mean, fossil fuel furnaces, the beauty of those is they can, your old dinosaur burner, they can throw, hundreds of thousands of BTUs of heat in the air in a very short period of time, simply because you just got to flame it lights and poof, so that can liberate that heat very quickly, whereas a heat pump has to work harder to extract that heat out of the outdoor air. Now, the good news about the heat pump, it's way more efficient, and certainly environmentally less hazardous, particularly if they're using renewable energy to offset the electric power generation. So I'll give you an example. Here's in Scottsdale, Arizona. I have an old traditional heat pump in this house that I'm living in while I'm building my new house. And so this is about I would say this probably is a 14 SEER piece of equipment. It's an older home. Home was built in the 70s. And the outdoor temperature at 47 degrees, my first register, closest to my unit, is discharge temperature is 104 degrees. I go to the second register, it drops to 99 degrees, and the third register is down in the very low 90s. So that's because the ductwork's inside the house, it's not insulated, and so you slowly drop temperature. But my point is that even with the outdoor temperature at 47 degrees, the hottest my register temperature coming out of that ductwork is 104. So, but the newer, more efficient equipment, you can get much higher performance out of that. So just to kind of review here, the advantages of the new variable speed inverter-driven heat pump systems is typically they don't need auxiliary heat backup. Not to say that you don't need emergency heat, but I'm saying typically you don't need auxiliary heat backup elements. In many of the climates, for example, the supply temps are much warmer than two-stage and single-speed systems. They can supply upwards of 110 degrees supply air temps. To my last person's question there, you can get upwards of 110 degrees supply air temperatures down to 38 degrees outside. Single-stage and two-stage systems might give you an 89-degree maximum temperature supply temps during that time. So just warn customers that traditional heat pump equipment is going to feel cooler coming out of the register. By using variable speed inverter-driven compressors, you can avoid adding 40 to 50 amps of panel load in some cases. I think the system that I'm using, some of these things, their amp draw will be less than 10 amps at more traditional loads. So that's really important when it comes to this grid issue. And particularly if you have solar and you're doing battery backup. So, for example, in most parts of California, the electric utility rates are 50 cents a kilowatt hour between 3 and 8 o'clock at night. So if your air conditioner is cranking away, which it usually would be at 3 o'clock in the afternoon, and you're on solar and you have battery backup, boy, these batteries you can't handle the big amp draw of these larger compressors. So having the variable speed inverter-driven compressors are much more battery friendly for those of you that are trying to offset those peak loads and flywheel through those peak times of the day. But with no auxiliary heat installed, the amp, we size the amp load and air handler. You want to make sure you size those appropriately, and make sure you pay a little closer attention to that. So bottom line is with no auxiliary heat installed. We size the amp load and air handler appropriately. Use 240-volt breakers, obviously, for that. And you can use these SIM lines that allow you to free up some space. So those of you that have existing homes, what I'm trying to say here is that oftentimes when you have existing homes and you have minimal panel sizes and you're trying to electrify, it becomes a little bit challenging, because how do you get enough breakers in the box and still meet all the electrical codes for fire and safety, right? And so I'll give you an example. I have a 100 amp service in this 1970s vintage 2,100 square foot home I'm living in, and we have an electric car, we have electric cooking, we have 2 air conditioning systems or 2 heat pumps, and we have a heat pump water heater, and we've never blown a breaker. So there are ways to, to make smaller panel sizes work. You just got to make sure that you meet all local electrical codes and proper inspections. All right, so questions?
Yeah, had a couple questions I wanted to interject before you get too much farther. There are questions about metrics. The first one from Gene: will HSPF2 give more accurate annual energy use estimates?
Yes. So great question, and here's why. The whole reason the Department of Energy made this change is because they recognized that, and this is largely due to the fact that in the last 30 years, we've almost converted 100% to flex duct. And as you'll see later in one of my slides, the impact that flex duct has on static pressure in systems. And for those of you that may not be into the technical side of this, I'm going to make this really super simple. But the bottom line is that the reason that this metric changed for seasonal energy efficiency 2 and heating seasonal performance factor 2 is because the old systems were overrating the efficiency of these units in terms with regards to how they perform in the real world. So what happens is we add flex duct and we have all these restrictions that impedes the ability of that unit to deliver heated or cooled air out into your home. And so what DOE realized is that, in order to drive the efficiency standards even higher, we better take a hard look at how these systems relate in the real world. So their test methodology to certify this equipment was not realistic to the way this stuff was really going in the real world. So DOE changed this to this new system so that we would actually get a better, more realistic view of what the efficiency of the equipment we're purchasing really is. So yes, to answer your question, it's a welcome change, and it's confusing, I know, but the bottom line is higher is better. Buy the highest you can afford. That's the bottom line.
And then that kind of is a lead into Carrie's question, which is, will the performance metric be labeled differently? So are we going to see SEER 2 on documents, or is it going to go to SEER even though it's SEER 2?
Oh, excellent question. Great question. Yes, it will be SEER 2, HSPF 2, and EER 2 for that matter. So absolutely. So that's what you want to look for, and buy the highest you can afford. Great.
All right. Thank you.
Others? So when we look at the options for these new variable speed heat pumps, and again, these are not your grandmother's heat pumps. So the heat pump that has the homes that I've had in the past, again, their efficiency, their recovery of capabilities are not even comparable to the systems that we can put in today. And the beauty of it is we have so many options. So for example, this looks like your traditional air handler, doesn't it? So this is a multi-position air handler where it can be mounted horizontally, can mount vertically. It's more like your traditional heat pump system. However, the guts on the inside are very different. They're all inverter-driven, variable speed, much more efficient piece of equipment. And then you might be familiar with this. This is where I'm broadcasting from today in Hawaii. This is I have I don't have heat pumps. We don't need heating over here in Maui. But here we can see here I've got a VAP coil that's mounted in my living space. There's another one in the bedroom, and we simply have two separate zones. Now we're mostly familiar with these as mini splits, so they've been around forever and used all across the world. We go back to this type of piece of equipment. This is what we would use if we had a more traditional ducted system in your home. But the bottom line is the inverter technology is the same. Now we go to where the house I'm building in Arizona. In each of the rooms, I'm putting in one of these ceiling cassettes. And these, again, are ductless systems. This is ductless, this is ductless, this is ducted. Okay, so we can use these inverter-driven heat pumps to be a ducted system, or it can be like your traditional mini split system, or it can be like these ceiling cassettes. This is what we call a one-way ceiling cassette. And you might be saying, well, Steve, it looks like it's ducted here. I see a duct. Now, this is where my ERV, so my ERV, it will bring fresh air into the home. It will dump it in here. This will pull this into the return air side of this coil and will heat it or cooling it. And the beauty of these one-way cassettes, they only protrude down from the ceiling about a half an inch. They're all 100% serviceable below. They have a condensate pump that will pump the condensate out to the outdoors. So I don't have to have any ductwork, and I can each room, excuse me, each room can have its own zone. So I can control the temperature of each room, and you can put up to 8 of these on one condenser. And so this allows, this inverter-driven system allows us to have very individualized zone control and draw at much lower amperages than your traditional, heat pump would do. So it makes it much more friendly to the grid. And these things are incredibly quiet. This one-way cassette, as it's called here, this is manufactured by Mitsubishi. This actually pushes air across the room. It can move air as far as 30 feet. And it has a vane that can direct air up and down, and has another vane inside that you can't see that can move the air left or right. So you have tremendous ability to circulate air and provide conditioned air where you want it. This is a builder friend of mine that is utilizing the same equipment, except this is what we call a four-way cassette. And this allows you to distribute air in 4 different directions. You'll notice this is a fairly large house. We have 2 4-way cassettes here. You'll notice this little bump out here is a little hard to see, but that's actually a infrared sensor. And you can even program these to direct cool air or heated air towards the heat source or away from the heat source. So again, they're incredibly quiet. These are ductless systems. So, and then we also have what we call, I don't know why. We also have what we call ducted systems too. This is a ducted coil that can mount up inside of a ceiling. So our return air ducts here. So this is maybe 12 inches tall and maybe 42 inches wide, maybe 36 inches deep. So these can be put almost anywhere. So you could do ducted or ducted systems, but still take advantage of the inverter-driven technology. So here's what I want you to look at. This is a kind of a fun chart. If we look at your typical non-inverter, typical heat pump system, air conditioning system, the thermostat calls for heat, it turns on, cools everything down, then it goes to this huge, big temperature swings. And it's drawing full power at all these times. So this is not exactly grid friendly if you've got 5 houses on a transformer that are all trying to do the same thing, right? So you have these big temperature swings. Whereas inverter-driven technology, it knows that, like I said earlier, it knows the temperature and the set point temperature is, it knows the outdoor temperature, it knows the temperature in the room, so it can actually compute and run this, the compressor at exactly the right speed to match the load. That's really important. These new technologies of heat pumps can actually match the speed of the compressor to the load. And so that way you have much lower amp draws, and much greater efficiencies and much greater comfort. So you don't have these big temperature swings, and that's really the advantage of these systems. They're quiet. You don't have these tremendous duct losses, and they do come in ducted systems, as I said earlier. But anyway, pretty cool technology. Question?
Let me check
I may
here,
be wondering
Steve.
what that was in the background. There's just some construction going on next door. Yes, Mike?
Gotcha. Okay, so under the new Performance 2 rating, do the single zone heat pumps still perform better than the multi-zone?
I would say, well, depends on what you mean by perform, but I would say no. In other words, because these units, they suffer from this. You know, remember the efficiency of the HSPF2 or SER2 doesn't have really anything to do other than the efficiency of the equipment. It doesn't mean that the installed efficiency is going to improve that much, because even if I buy a traditional piece of equipment, like for a standard heat pump, and if it's just a big compressor that's a single speed compressor, it may have a high SEER rating or may have a high HSPF rating. And this is an important distinction here, but that doesn't mean it has the capacity to be variable speed. So you're still going to have these big temperature swings, you're still going to have these big amp draws, and you're still going to have good bit more, you're going to have more power consumption, even though it's more efficient than their counterpart. The beauty of the inverter-driven technology is that you can vary the speed of the compressor based on the real load. Now, you're probably asking, what's the downside? Well, they cost more money. They're much more complicated in terms of, or much more sophisticated, I should say. Not necessarily more complicated, but most definitely more sophisticated in their capacity and ability to cool. So yes, you can buy a high efficiency piece of equipment and it'll perform just like this. You won't get near the comfort out of it. But if you go with the equipment, like any of these different variations of this, you're going to get a much more efficient delivered cooling, you know, much more efficient delivered cooling. Now, this is an important chart here. Check this out. This is a cold climate heat pump. And it is a myth that heat pumps don't work in cold climates. So here's an example of one manufacturer's. It can deliver 100% of capacity at 5 degrees, 76, depending upon the equipment, 76 to 93% capacity at -13, and operation to -18 below, and even as low as 31 below zero. So that's the beauty of this equipment. They figured out some clever ways to be able to take the waste heat off the compressor in order to recover that waste heat in order to make it work when it's really, really cool outside. There's an example in Colorado, very cold weather. Here's another one where one person said that, hey, it was -22 and still the inside of his house was comfortable. Now, I'm going to talk a little bit more about how we got to get there to do that, because it's not a matter of just slapping in a piece of equipment, but here's another example of, you know, at 11,000 feet elevation and, you know, replaced a 15 kW electric resistance with a heat pump. So, you know, there's another example, but here we go, -24, that's pretty chilly. And it's at 3 days below -20, and the systems, you know, held up and did pretty well. So I'm really impressed by these systems. This is what example of what I'm putting in my house. Obviously, in Arizona, I don't need a heat pump. I mean, excuse me, I don't need a cold climate heat pump, but certainly we need heating there because it gets down in the 30s with it. All right. So a couple of things that's really important to slow down here a little bit and get into how we set customer expectations. There's a big difference between being able to get one of these systems installed perfectly and getting the kind of performance that you can get versus what might typically happen in the real world if we're not paying attention to some really important installation issues. So typically complaints we get with your traditional single speed and 2-speed equipment. So when we talk about electrification and on the heating side of this, you can say, okay, I'm going to go and just replace my heat pump with your standard single speed or 2-speed equipment, which probably the majority of the equipment being installed out there, this is probably where people are going to go, perhaps, just because people aren't aware of how valuable and how effective this variable speed equipment is. But let me just say that setting customer expectations is really key to reducing callbacks for those of you that are builders or those of you that are HVAC contractors. So what happens is what's traditionally happened in areas like, for example, where I used to live at in California, there were moratoriums on gas hookups. And so people would replace their gas furnace with their heat pumps. And they said, well, wait a minute, we're not happy with the comfort we're getting out of this, because we're used to, being able to come home and turn on our furnace and heat our house in 15 minutes. And heat pumps just take longer to do that. So some of the complaints are, it takes too long to heat up my house. Secondly, as we talked earlier, the registered discharge temperatures are lower, so people would say, wait a minute, it feels like cold air coming out of the system. And in some cases, if their electric utility bills are high and they're running on peak load, they during peak periods, their bills were higher than they thought. So it's really important, number one, wherever possible, to utilize inverter-driven equipment, because you could better match the loads to the home to the equipment, but also make sure you explain to customers that you just can't turn your thermostat up and expect your home to get heated in 15 minutes, and also recognize that the discharge temperatures coming out of the registers might be a little lower, particularly if the HVAC contractor didn't take the time to seal the ductwork, or maybe didn't take the time to insulate the ductwork. So let's just say, and I'll explain this a little bit more detail, show some real world examples. So, Mike, do we have any big questions?
Well, actually, for clarification on the prior question, apparently in the HSPF, no two, okay, so just HSPF ratings from the past, single zone variable speed heat pumps would typically have an HSPF that was 30% higher than a multi-zone variable speed. And the question is that still going to be true with HSPF 2?
Great question. Yes, absolutely. So remember, these are here. Let me back up a little bit, make sure I'm being clear on this. These efficiency ratings, the only change between the 2 and the previous version is the fact that they're trying to be the testing for the efficiency better replicates real world performance the way these systems are installed in typical homes. So yes, it will be more efficient. Anything in the new system, the new rating is going to be more efficient than the old system. So how annoying is that noise in the background, Mike? Is that really bad, or do I need to move to a different location? I can really easily do that.
No, I think you're fine, and I appreciate the clarification on that prior question.
Okay, yeah. So the new rating is going to be more efficient. So keep in mind, let's keep in mind like this: the reason the new rating was developed was because they recognized that the way these systems are typically installed in homes, the ducts have a lot more restrictions than the initial test really showed. So it made the systems, the old method of measuring efficiency, made them look like they were more efficient than they really were in the real world. So they made this adjustment so that these would have more real world efficiency. More, I guess, a representation of a better real world efficiency. So the bottom line is the comfort concepts we want to remember is that with heat pumps, registered discharge temperatures can be lower, which can be a function of outdoor air temperature. Not necessarily the case with inverter driven. It will be a little lower, but certainly can be. Higher airflow means lower register temperatures. So in other words, if we have more than 400 CFM, cubic feet of air per minute, you might tend to have lower register temperatures. Longer recovery time than fossil fuels. That's just something we have to make sure people are aware of. This is important. Your enclosure leakage rates, in other words, you have a leaky home, has a greater impact on your recovery time. That's why the setback question was so important. If I have a really leaky building enclosure and I have poorly insulated walls, that system has to work longer to recover that setback time. So that's why they typically don't recommend setbacking thermostats at night. Duct leakage and insulation has a greater impact on comfort, and really important to get the enclosure right. So let's talk about a few items here. Making sure that when we talk about a building enclosure, obviously we're not just talking about insulation, we are talking about air leakage as well. And so some cost-effective enclosure tips. I'm a big believer for those of you doing new construction, certainly advanced framing. That helps a lot to reduce that thermal bridging. Whether it's new construction or old construction, we want to do a really good job of air sealing. We want to be down at that half an air change an hour to maybe to 3 air change an hour, depending upon your climate zone. Our windows, we want to have 0.25 U factor, 0.25 solar heat gain coefficient or less. Certainly lower is better in both those numbers. Our indoor air quality controlled to control our ERVs. So I'll show you some examples of that in a moment. Common sense electrical approaches, sorry about the typo. And then of course, high performance attics. So check this out. This is not advanced framing. So how in the world can this building enclosure be very effective when it's so overframed? When you got, framing factors here, this is probably close to 35% framing factor. The homes that we were doing out in the Central Valley for the book we did for the Energy Commission, we were getting homes in the 11 to 13% framing factor range. Without any additional impact on structural integrity. If you want a great resource for advanced framing, the American Panel Association has a great guide. You can just go to apawood.org, and you can download this advanced framing guide. It's a really great pictorial guidebook. It's even got code references in it. So if your code official is not really buying what you're doing, you can show them where it meets the code. And then just paying attention to the details. So for example, here, here's where the builder really was paying close attention to air sealing. They used this, air sealing material around every crack and gap. But what do you see that's wrong with this picture? They didn't pay very close attention to their mechanicals and their electricals. The exterior walls, and you never want to put ductwork in exterior walls. Can you imagine what this would do to your discharge temperature in a winter climate if you have basically this cavity is going to be uninsulated unless you happen to have some exterior insulation. So now the discharge temperature coming out of this ductwork, because it's on a cold exterior wall, is going to be much lower than it would have been had this ductwork would have been placed on an interior wall. Notice all the plumbing. Notice all of the tremendous amount of just mechanical, electrical that we have in these spaces. So there's a lot of simple things that we can do in the building envelope during construction that allow for better heat pump performance in terms of discharge temperatures at the registers, in terms of recovery time, in terms of overall capacity. Attics, for example, we talk about high performance attics. Oftentimes we never air seal interior plates. So for example, here, I'll give you a great example. This is an older home that I used to have in California. It was a 1970s vintage house, 1976. And I decided that I had a bat problem, so I took care of that. And then I air sealed my attic. So my blower door test before my attic was air sealed. This is for a 3,400 square foot house. Was 4,460. After I air sealed the attic, which is basically just air sealing every nook and cranny in the attic with spray foam here. And I didn't spray foam the whole attic. I just simply spray foam the interior, exterior wall plate connections around any penetrations. It dropped to 2180. So get this, folks. I reduced the air infiltration rate on my entire house by cutting it in half just by air sealing the attic. And the house was on crawl space. So lots of things we can do. For example, here, the type of connectors that we connect. See these hurricane clips? They actually shim out the drywall about 1/4 of an inch. And so that creates a pretty big air leak through here. And also notice the number of fasteners, 1, 2, 3, 4, 5, there's 5, 10, 6, almost 20 fasteners it takes to mount this hurricane clip. Here's an SD fastener. We simply take one of these screws and screw up through the stud into the plate, into the truss for hold down. And again, your local codes require different requirements based on where you're at, so pay attention to that. But what I'm saying is this countersinks in there so you don't have this big attic bypass. Another thing, here's a great example of what I did for my house in Arizona. I put 1 inch, get this, I put 1 inch of Thermax foam sheathing, R6 insulation over the top of my roofing membrane. So I had a peel and stick roofing membrane on this hip roof. Put the 1 inch of foam down, polyiso R6 over the top of that. This will be the battens for my metal roof. Now check this out. This is part of it I left uninsulated on purpose, part of it I insulated. So this is the uninsulated portion, and it's about 110 degrees outside. This is the insulated portion. This is the uninsulated portion. So this is where the foam's at. This is where the foam's not. Look at the difference. 140 degrees. So there was almost a 35-degree temperature difference between the insulated portion of the underside of my roof deck and the uninsulated portion. So at about $1 a square foot, I reduce the surface temperature on the bottom side of my OSB by 35 degrees. So that's going to have a huge impact on me being able to kind of flywheel through those peak times of the day. And so that's what I meant by being able to design your building enclosure so that you can make it more peak load friendly. And what's happening throughout the United States, electricity that's generated during these, on peak times, it's very valuable. Utilities are really having a hard time keeping up with in some cases, some parts of the country, keeping up with these peak loads. And so being able to make your house more peak load friendly is going to save you a lot of money. As I said, in California, for example, the peak load rates are 50 cents a kilowatt hour. In Arizona, where I live, on peak rates are about 28 to 29 cents an hour versus the off peak, which is about 12 to 13. So questions, Mike?
Yes, we do, Steve. Got a couple of them. So one of them is actually going back to this single head and multi-head question from before. But this one's coming in from Jonathan because he's asking kind of in a different way. He's saying that right now the multi-head systems are not as efficient as the single systems, and he's wanting to know if that will still be the case.
Yeah, well, it depends on how you define efficiency. He brings up a good point. Yeah, so the more heads that you have on one compressor, the less efficient it is. So if I have one compressor and one, let's say a VAP coil or heating coil, that is going to be the most efficient. When I start adding more additional units to each compressor, the efficiency drops because you have, much more, you have more refrigerant lines and so forth. So that's true. But when you look at the overall efficiency and not just the nameplate efficiency, where you're looking at in terms of delivered comfort and also the balance of overall cost. I mean, for my situation, I'm putting in multiple condensers. I have cases where I only have 2 on one condenser, but that's just the system I chose to design. Not everybody might be able to afford that, but my point is that you want to look at delivered comfort, so and delivered efficiency. So, for example, I may have maybe a nameplate number that's less efficient because I have 4 units, 4 heads on one compressor. Right, but the overall fact that I can vary that zone by zone and I can turn that temperature on and off room by room, my overall cost is going to be much lower. Does that make sense, Mike?
Yeah, no, it does. And I wanted to get to another question as well from Eric. He wanted to know, have you used insulated concrete forms or structural insulated panels for thermal enclosures?
Yeah, matter of fact, if you're into this, we have a webinar. PG&E, Pacific Gas and Electric, has me do a SIPS webinar on this kind of topic. I think SIPS are great. We've built, not for my own personal use, but built a number of SIPS projects. For the International Builders Show, we did a few projects where we used SIPS panels. A couple projects we did with Sarah Susanka. And yeah, so I'm on SIPS. And the insulated concrete forms, I personally haven't used them on my personal house, but I think they're fine. In fact, one of the Vision House projects, CR Hero, if you go to the website, the Vision House websites here on Green Builder Media, you can look at his project, which was an ICF project. Well, yes, so I think those can work great.
All right, great. Thank you, Steve. Keep on going.
Yeah, so a couple areas I think in terms of getting air infiltration right, big things that I see people miss. They typically will air seal this side of the plate, but you need to air seal top side of the plate too. Actually, more air infiltration comes over the top of the plate than comes underneath the plate. So that's important, like I mentioned earlier about air sealing the attic. Pretty easy to do. Spray foam now, they have low GWP products that are down less than 5, where these products a few years ago used to be up in the over 1,000. What we mean by global warming potential, CO2 has a global warming potential of 1, but these products are much lower GWPs, and so they do a great job of air sealing. This is a froth pack system that DuPont makes, and it's has an R value of about 6.2 per inch and has a low GWP. So just, here's my wall system. I'm simply doing like a stucco wrap material over the top of my OSB, and then I'm going over that with 1.5 inches of polyiso for my exterior insulation. It's tongue and groove, and then I'll go over that with a rain screen lath system, and then stucco is very popular in my area, so I'll go over that. So I'll essentially have R12 on my interior wall system, and then this will be another. This is another R10. I'll have a little bit higher than that because I'll probably backfill with some blown fiberglass because my walls are 2x6, and then go over that with stucco. All right, so really important to pay attention to how we install these systems. I can't emphasize this enough. If you look at this picture here, what do you see? You see all those black marks around the insulation. You know what that is? That's not mold, that's dirt, and that's because the duct is leaking. So it's not uncommon at all in older homes to have 300 to 400 CFM worth of duct leakage, or almost 25% the entire system's efficiency being lost through leaks in the ductwork. And with a heat pump, it's really important because if I'm losing 25% of my heat to the outdoors, that means I'm not delivering that to the inside. And so that means the recovery time is going to be longer. My comfort levels are going to be impacted. And so with heat pumps, it's really important to air seal. Oftentimes we see people put in, replace systems with heat pumps when they don't bother to insulate the ductwork. So you can imagine if this is in a crawl space, this metal duct is a pretty good radiator. And so that means my registered discharge temperatures are going to be lower because nobody took the time to insulate the ductwork. So what we would do here is we want to seal the ductwork with some mastic sealants and then go over that with some insulation. Or you could use a system like AeroSeal, which seals the ductwork from the inside out. It's kind of like Fix-A-Flat. But my point is, anytime you're doing any work on your home, and particularly if you're retrofitting your home or swapping out a gas furnace or fossil fuel furnace for the heat pump, you want to make sure that you air seal the ductwork and insulate the ductwork. And this is part of the proper inspections that you want to do, before you ever do this installation. So it's not just a matter of going out and slapping in a heat pump and saying everything's going to be good. You really have to pay close attention to all of the details. And then getting the airflow right, making sure that you have a licensed professional size your system based on whether you're heating or cooling. And this is really important because, you want to make sure you get the loads right. You want to make sure you get the ductwork designed right. So typically you use ACA, the Air Conditioning Contractors Association, Manual J, current version, to calculate the loads or equivalent software. And then use Manual D to design the ducts, Manual S to select the equipment. But spend the money on a professional that can help you design these systems to get the proper airflow you need. And then, you have to pay attention to how the ductwork system is installed. When you look at these distribution systems, and one of the reasons why we switched from the old system of SEER and HSPF to SEER 2 and ER2 and HSPF2 is because this is the types of things we saw in these systems. And so the installation has a much bigger impact on performance for heat pumps than it does conventional systems. Why? It's just because heat pumps, they simply have to take the heat out of the air, so they have to work a little longer than their dinosaur burner, counterparts. Well, that's why we pay attention to those installation details. In fact, a lot of studies have been done on this and found that, we're looking at some of the traditional shortcomings in terms of, 3/4 of the time, they don't have adequate airflow. They don't use the proper method for evacuation of refrigerant lines. The failure to use recommended charging methods. All these things are really important.
From the same in-row study.
So this, for example, here, if we look at this capacity of these systems, my system's going a little nutty there. Bottom line is, when we're looking at the capability of these systems, you could save easily 20–25% or more just by getting installed right. Now let's take a look at summer heat gain, because this I think will really impress you in terms of some work that the California Energy Commission did a number of years back. They just said that if you look at the average amount of square footage of ductwork in an attic, it ends up being about 40% of the floor area of your home. So if I have a 2,000 square foot house, having my ducts in the attic, what kind of penalty is that? So what I'm getting at here is that we're trying to get summertime performance out of our heat pump air conditioning system, we need to pay close attention to one of the biggest kiss of death we can have in our system is having our ductwork up in our attic. So we did some basic math here, and let's just say we got a 2,000 square foot house and we got an attic temperature of 140 degrees, and our ductwork is insulated to 2.1. That's an older home. That's a home that has old ductwork in it. So that ends up being a total load on that ductwork of 2.5 tons. So that means if I've got a 4-ton system, 2.5 tons is just to offset the heat gain in the attic. So that kind of gives you an idea of just how ugly attics are in terms of contributing to the overall comfort and cooling load of a system. Now, if we take this and say, let's go to an R8 ductwork, which is required today, all right, that ends up being about 0.67 tons. Okay, so it's still, you know, almost 3/4 of a ton of air conditioning just from that additional heat gain. So doing non-vented attics probably makes a lot of sense. If you're going to have ductwork and you're going to have equipment up in your attic, which I highly do not recommend, at least consider some type of a non-vented attic where we basically insulate the bottom side of the roof deck with typically it's going to be most climate zones are going to require that you have a non-vapor permeable insulation. Typically that's going to be spray foam. In the colder climates, that would be closed cell spray foam. In the warmer climates, that would be an open cell spray foam. Check your manufacturer's recommendations. But the point is, if we have equipment up here, it takes a heck of a penalty as a result of that. Like I said, anywhere between 2.5 and almost 3/4 of a ton of air conditioning. So summary, make sure the unit's properly charged. One study showed that 62% of the time, another, almost 72% of the time, these systems were never charged properly. So look what happens to the performance of these systems if they're not charged properly. We're talking about charge, we're talking about the refrigeration that goes into the system. So let's say we're 100% of charge, and we're 100% capacity and 100% efficiency. But let's look what happens if we're 25% undercharged. If we're 25% undercharged, our capacity drops by 25%, and our efficiency, drops. Look what happened, and so we paid for a 4-ton system, but we get a 3-ton system, right? And this goes back, this is data we've known for 30 years. Likewise, if we tend to overcharge by, 25%, our capacity again drops by 25%, and our power usage goes up to 10%. So we pay 10% more to get 25% less. So I can't emphasize the importance of making sure that we charge this appropriately. Now, Purdue University did some more recent studies and found out if we look at over here at 50% of refrigerant charge, and we look at overall capacity, look at the curve, how much it drops off. So we go from 100% to less than 60% of capacity as a result of refrigerant charge. When we look at refrigerant charge on our efficiency, again, look at that. We go from 100% down to about 60% if we're, undercharged. So I can't emphasize the importance. And then the seasonal efficiency ratio drops off dramatically. So getting the appropriate charge is important. So that means that they're using digital gauges, not analog gauges like we see here, that they're using, they're weighing in the refrigerant, that you have qualified people who know what they're doing to make sure that we're putting in the right amount of refrigerant, that we're just not filling it up, right, to make sure that the refrigerant charges properly. So getting the sizing right is good for comfort, for energy efficiency, performance. The system sizing is really important that we don't use rule of thumb measurements. If somebody says it's, that you're putting a system in and it's going to be, 400 square feet for the ton, you need to find a new person, because you might have the same size square footage as your neighbor, but your house may have, double the square footage of glass that faces west. You're going to have totally different loads. And so that's why it's really important to make sure that we size the equipment right. And the beauty of inverter-driven equipment, because it's computerized and based on the load, it's much less, much more forgiving, much less of an impact on overall performance. So bottom line is no more than 10% greater than manual J-curve version. We want to use indoor design temperatures that are realistic for the area that you live in. All an HVAC contractor has to do to oversize your system is give you a lower design temperature for the summer sizing. Okay, and then indoor and outdoor coils need to be matched. Duct size according to manual D. And of course, make sure that our return air and supply air ducts are designed according to manual D specifications. Duct insulation has a huge impact on overall performance. Duct leaks can create pressure differences that create air infiltration, exfiltration across the building envelope. Like I said, it's not uncommon to have 300 to 400 CFM of duct leaks, and duct leakage, of course, wastes energy. Now check this out. This is really an interesting chart. We talked about this a little earlier, but when I talked about the compression rate, so in other words, if you take and stretch your ductwork, so what I recommend people do when they're installing their ductwork is they put a metal elbow, say at one end or coupler, and they fasten that to a framing member. Then they pull the flex duct taut, like you see here, and then use another, let's say, metal elbow or coupler, and fasten that to a framing member. And the difference is, if you look at a 30% compression rate, you have 4 times the friction loss. Whereas if you have a 4% compression rate, which we stretch the ductwork, like I said, you have 1x the friction loss. And then 15% compression, you have 2x. So, being able to pull this taut is really important. And then also keep in mind, flex duct, it can be, really hard on your system and create much greater static pressure differences that make it harder for that system to push air throughout your house. So for example, if we just look at a bend like this, this is the equivalent of this duct length is actually 10 feet. But because of the 290s, that gives you an equivalent length of this duct of 50 feet. So really important to recognize that the number of bends that we should have long sweeping bends. Use elbows here instead of the flex duct. Makes for a much better efficient system. And this is really important for heat pumps because airflow is what it's all about. Greater the airflow means greater the comfort. And so making sure that we stress the ductwork, we use elbows at these conditions and metal elbows instead of just bending the flex duct. Also, inspection is really, really important. And then these type of grills are just the kiss of death in terms of proper airflow. I'm a big believer that you use commercial grade grills. These are these egg crate grills that you can get these up to 2 inches thick, so you can put pleated MERV 13 filters in, which filter 85% of all the particles that are less than a few microns, which are really good in terms of enhancing the indoor air quality of your house without creating great pressure drops. Here's some supply registers. This is what I have in my own home. Even my older house, I replace these. So these give you airflow that broadcasts the air much deeper into the room, with much greater restriction than you see with these types of, let me go back here, with these types of grills. Okay. And again, look out for these types of problems like this. This is just the kiss of death. When you see these types of restrictions, and it has a huge impact on any system performance, not just heat pumps. But these are the kind of things that we need to pay close attention to. Here, for example, new construction, they got a 12-inch diameter joist, a 10-inch diameter duct, and a 4-inch sewer line. How thick could this be? So how much air can possibly come out of here? So these are the things we have to pay attention to when we're either, obviously in cases where we're building new construction, but even where we can see the ductwork when we're retrofitting, to pay attention to that. Keep in mind that pre-planning is really, really important. Here, for example, plumber always wins. The ductwork was put in before the plumbing was installed, and therefore we get substantial compression. That's not going to be able to deliver the adequate airflow to the room. Proper supports, instead of a 1-inch hanger, this should probably be closer to 3 or 4. If you can, don't suspend your ductwork from the attic. In some places, code officials require that. I never understood why, but anyway, this is not what we want to try to recreate. Obviously, these things are important. So duct runs should be straight with no kinks or crushed areas. They should have wide angle sweeping turns with, I believe, metal elbows, obviously sealed with mastic sealants, flex duct connections, the boots with duct ties and the appropriate tape, and duct leakage. Always meet your local standards, which is the new codes now are doing a much better job of requiring that we eliminate duct leakage. Here, for example, this is where they just put a couple sheet metal screws. There's no air sealing where the boot to floor connection meets. There's no air sealing that takes place where this duct's at. Again, example, the dirty insulation. So here's where you do it right. You simply pull the liner over the boot. You put a few wraps of UL 181 BFX tape, put the drawband on, pull the insulation over that, add another drawband, you've got a really nice tight connection. Typically, the codes require that you use one of 3 types of duct tape, not the standard gray type duct tape that we use to fix everything in the trunk of our car, right? That we keep for emergency use. But this is the UL 181 BFX tape. It's acrylic, has acrylic-based adhesive. This has got butyl-based adhesive. This is a metal tape with acrylic-based adhesives as opposed to rubber-based adhesives, which dry out and cause problems. Questions?
Well, actually, I was going to put out a last call for questions, and we can get to as many as we have time for. But I don't have any at the moment for you, Steve. But when we get to the end, we'll take whatever we've got left.
Sure, and then I'm going to get into heat pumps and also talk a little bit about induction cooking and heat pump clothes dryers. I got some new info on that. So when I talked earlier about fresh air ventilation, it's required in almost all the codes today. And earlier I said one of the real things that would be helpful in electrification is to be able to have a very efficient ERV, but have it controlled by monitoring real indoor air quality. So these ERVs are energy recovery ventilators. They also have what we call heat exchangers, another term for heat recovery ventilation. But for example, the system I'm putting in my house, for example, it'll have the ability to take outdoor air at 110 degrees, and then it takes the stale air from the building, let's say at 75 degrees, and then it will recover that energy and bring me preheated air in at 83 degrees, and then it'll exhaust that air at 105. So these systems use very little watt draw, but the beauty of these systems, it allows you to bring in fresh air and recover the energy that you pay to heat and cool your homes. And these are getting more cost effective every day, and but it allows you to have fresh air ventilation without the penalty of having to reheat and recool all that air you bring into your home. Now, I also mentioned that the ability to be able to monitor your true indoor air quality and then run your ventilation system based on what that air quality is, rather than say just an ASHRAE CFM per minute standard. And so what I've been experimenting with is this system here, which is basically has a small sensor, and the sensor talks to the cloud. It analyzes my indoor air quality. You can see here it's green, so things are good, but it analyzes the indoor air quality, and then we'll send it to an app. And so this is right off my phone. It'll tell me what my humidity is, what my overall indoor air quality status is, what my CO2 levels are, what my total volatile organic compounds are, and what my PM 2.5 are. So PM 2.5 are those particles that are less than 2.5 microns. A micron is a millionth of a meter. And so when the problem with these PM 2.5 particles is that they have the ability to bridge the gap between your bloodstream and your lung tissue. So when you're looking at automobile exhaust or even cooking, for example, inside your home, it can generate both electric or gas. It can generate PM 2.5. Obviously, volatile organic compounds are things that we don't want to have high. But anyway, this can actually monitor this and actually operate my ERV based on my real indoor air quality. So if I don't have an indoor air quality problem, I'm not, over ventilating my house. And that's the beauty of these types of systems. So what they can do is they can control my range hood, they can control my ERV. I can have individual switches in each room, which will monitor the indoor air quality and kind of let me know if I've got polluted air, it's red, or if it's above levels, it's yellow, or if it's everything's good, it's green. But these systems are really clever in terms of their ability to be able to actually monitor indoor air quality. And the reason why I like this is that I'm not paying to overventilate my house when my indoor air quality is not necessary to provide overventilation. So how much energy? Well, let me just stop before I get into heat pump water heaters. Any questions on these types of systems, Mike?
Well, we have one question from Nicholas, and I don't know if this is an entire webinar or if there's something you can kind of summarize, but he's wanting to know the pros and cons of duct versus ductless in new construction.
Good question. My advice is unless you can really, ducted systems can work very well as long as, number one, you size them appropriately, number two, you install them correctly, and number three, you test to make sure that your duct system is airtight, and then number four, any ductwork that is located in unconditioned spaces, you either bury the ductwork or heavily insulate it. I highly advise you that. So you can make ducted systems work. There are ducted systems that can work very well and they can be very efficient. The reason why I tend to lean more towards ductless systems is because you just have less potential for problems. The reason why I used all of these, I used 7 different of those cassettes and mounted in my ceiling mounted one-way cassettes is because I wanted to control the heating and cooling in each of my rooms individually. I didn't want to have to heat and cool rooms that I wasn't going to be using, for example. Or I want to be able to heat and cool those at different levels based on its occupancy. So I wouldn't say that ducted systems can't work. I just think that ductless systems overall are a little less problematic.
All right, very good, Steve.
Okay, so let's talk about heat pump water heaters. If you have an electric water heater, you can literally save 75% on your bills over an electric resistance water heater. Obviously, when you compare them to gas, you know, they're going to be more environmentally friendly because, you know, you could offset that electric use with renewable energy. But the bottom line is they're 2 to 4 times more efficient. The savings really depend upon your fuel prices, also your lifestyle, your hot water demands, those kind of things are also important, and the climate you're in and where it's located. So here's an example. I replaced my electric hot water heater with a heat pump water heater. This is in my garage. This is what the two look like. The difference. This drew 4,500 watts. And had a COP of 0.85 to 0.93. This in heat pump mode draws only 400 watts at a COP of 4. So when you're looking at over the course of a year, you're looking at roughly $100 versus over $400. So heat pump water heaters, if you have electric, can really save you a lot. Now here's an example of my usage. I have an app on my phone, and the beauty of these things is that you can actually track your water usage, heating usage, your energy usage. I can even switch them to vacation mode while I'm gone using the app. But on average, you could see that in January, my hot water usage probably averaged in that, roughly that 2 to 2.5 kilowatt hours a day. My water heater is located in my garage. Notice for the January 2022, I use 79 kilowatt hours of electricity to heat my hot water, just using the heat pump mode. Now look at this in June. I used 40 kilowatt hours. Anybody want to take a guess why? With an average of less than 1.5 a day? Because I'm in my garage. And so the garage gets upwards of 95 degrees. So let me go back here and show you this. Hang on a second, I find it. Sorry, there we go. So this being in my garage, my garage is like 95 degrees. So the COP of my water heater went way up because it's so hot. Where in the winter months, it's probably closer in the 40 degrees range. So bottom line is that no matter what time of year it is, you're still saving energy over traditional systems. But I just thought you'd find this fascinating to see, how much less energy you use with one in the garage in the summer versus the winter. So heat pump water heaters, they're, a lot more energy efficient. So again, 75% less energy use, or a quarter of the energy you were using, 4 times the efficiency of gas or electric. Okay. Now, a couple things to note. Electric resistant elements can heat about 20 gallons in an hour. Gas can do it in about 15 to 20 minutes. So again, fossil fuels have the ability to liberate a lot of heat in a short period of time. The bad news is not quite as good for the environment. Heat pump mode can typically average, when a heat pump water heater is in heat pump mode, about 8 gallons per hour, and even less if your temperature where the water heater is at is below 60 degrees. But typically people take their showers in the morning or the evening, and then it has time to recover. So there are 2 of us, we got by with a 40-gallon tank and never had any issues just operating in 100% heat pump mode. So electric resistance heat, turns 100% of the electricity into heat. We typically measure the efficiency of water heaters by energy factor. That was replaced by uniform energy factor in 2017. Again, it was just a way to create a more realistic rating. That's the reason they changed it. DOE changed it from UF to UEF. It just simply provides a more consistent, accurate way to measure the efficiency and performance of water heaters across all brands. UEF, basically, the higher the number, the better it is. It's the efficiency of the water heater to convert energy into hot water. And then, of course, typical gas and electric UEF ranges, for standard equipment is between 6.5 and 9.5. Heat pumps can be between 2 and 4. So obviously, heat pump water heaters are much more efficient. And you can go online and you can look at a variety of these. This is what I installed. It has a UEF of 4, so it's pretty efficient. I know it looks similar to a COP, slightly different, but close enough. And then it's important that you recognize that to set these up is important, because if you set this up and you're going to run this on high demand all the time, your customers won't see any savings. In fact, you might even see more energy use. You want to have this operate on heat pump mode as much as possible. And second to that, energy saver mode. And all the different manufacturers are pretty close to this. I mean, they all have a similar interface. They either run at heat pump mode, hybrid mode, a high demand mode, or standard. And you could check whatever manufacturer of your choice, but the bottom line is I run mine in heat pump mode and never had any issues. It is important to recognize that if you're putting one of these inside your house, that you need to have a room that's roughly 700 cubic feet. So that's roughly 7 by 10 by 10, and you can have a door on it, but you need to have enough space so this thing can breathe and extract the heat. You could do louver doors, that would certainly help. Or you could duct the system. They make these to where you can actually duct to the outdoors or duct to the indoors and bring fresh air in. You can undercut. Here, for example, they're saying this manufacturer, this is a Ream system, they're saying if you undercut the door by 3/4 of an inch and it's 24 inches wide, and you could duct this so you could supply that cool air. The beauty of heat pump water heaters, in the summer months, they cool your garage. You could even run that duct inside your home, so you could take that roughly 4,000 BTUs per hour and use that to cool your house. So that's the beauty of heat pump water heaters. They're basically a small air conditioner. And then you could even duct these where you have air coming into the unit and out of the unit, so there's no energy penalty whatsoever. You can even, some manufacturers have these ducted kits that you can purchase, and again, so you can add some additional cooling capacity to your house. This is what they kind of look like in the real world, these kind of ducted systems. It's a really important installation-wise. You give it plenty of room to breathe. Here, for example, they put it right up against a basement wall. That's not good. You want to have a room like over here on the left. If there's adequate room, make sure you have room to change the filters. This is a little air conditioning system, right? It's a heat pump, so it needs to have the capacity to be able to filter the air. So we want to make sure those filters are in fact clean. And then make sure that many codes will require anti-scalding devices. So we want to make sure that we take care of that and insulate the piping according to national codes. And then also keep in mind where you place these units, put out 49 to 65 dB. So if you're concerned, about noise, you might not want to put one of these near a bedroom or other noise sensitive locations. So be cognizant of that. They are a little bit more obviously going to be noisier than a traditional water heater. So questions about heat pump water heaters?
Just one comment from Jonathan. He said, hey, don't they also dehumidify?
They absolutely do. Thanks for bringing that point up. They absolutely dehumidify. They take any air conditioner, obviously takes moisture out of the air. So that's a very good point. Thanks for reminding me of that.
All right.
Okay. So let's move forward into cooking and also some indoor air quality concerns that you might want to be cognizant of. Let me just say this: all cooking stoves create some pollution. Gas stoves are about 40 million homes in the United States, and I can't emphasize the importance that adequate ventilation is critical to improving indoor air quality, whether you have an electric or gas stove. However, there are some more recent concerns, some studies that have come out that have, starting to show that cooking with gas does indicate elevated levels of NO2, nitrogen dioxide. So one study here from Lawrence Berkeley Lab showed that 4 of the 9 homes had higher NO2 levels than you would like. In fact, a quote is that exceed the national ambient air quality standard of 100 parts per billion. So, it can be a lung irritant. Things we're concerned about with gas stoves is particulate matter, and that's gas and electric. So when you're dealing with PM 2.5, those particles 2.5 microns or greater, both gas and electric stoves emit those products. That's just a byproduct of cooking. And so proper ventilation is really, really important. With gas stoves, of course, there's more nitrogen oxides, which are considered a lung irritant and can be higher than outdoor levels. Carbon monoxide, benzenes and BTEX, that's a series of chemicals that are of concern. A study by the National Institute of Standards and Technology found that cooking with gas burners set on high heat emitted lower levels of formaldehyde, while cooking with the gas burners set on low levels, simmering, emitted higher levels of formaldehyde. And I thought that was interesting because at higher temperatures, the formaldehyde tends to be consumed as quickly as it was formed, but at lower temperatures, less formaldehyde was consumed, allowing it to accumulate in the air. And then, of course, carbon dioxide. So these are the things that they're concerned about. That's why ventilation is so important. There's also been concern about the leakage of gas stoves. This was a 53-home California study where they found that more than 3/4 of the methane emissions were measured and originated during off conditions, which is disturbing. So even when the gas stove is off, it may be leaking, contaminants in the air, particularly if you have pilot lights, of course. They're less and less frequent as we see in, homes today, but still, there is some concern about this. So the California Energy Commission has done a lot of studies on this, and, they, with regards to range hood ventilation. So what I'm trying to say here is if you have any type of cooking you want to use, you want to definitely use proper ventilation. And unfortunately, we only use, if these studies are correct, range hoods about 36% of the time in homes and 28% of the times in apartments. And not all of the times are these systems ducted to the outside. So that's a little disturbing. A study that was done by the California Air Resources Board found that of the number of homes, they did 92 of them, 48%, or 92 homes, or 48% of the 193 homes, they only use it less than 50% of the time. And the reason, they felt like too noisy or didn't even think about it. So I can't emphasize how important it is, particularly if you have gas equipment, to make sure that you are using proper ventilation. And they've set some new standards around that. But first of all, let me show you a little bit about capture efficiency. So this is what you want your range hood to do. You want your range hood to be able to get both front and back burner capture efficiency for adequate removal of pollutants. And so I can't emphasize that enough. And when they looked at some simulations that they did, they found that the simulation suggests that requiring a minimum capture efficiency at least 70% is needed to avoid unacceptably high levels of NO2. Which is average 1 hour concentration of 100 parts per million. In other words, the outdoor limit for EPA is 100 parts per billion. So we don't want to go above the outdoor limit indoors, right? So when we look at the California requirements now, they basically say that if you have a hood over an electric range, and this is ducted to the outdoors, okay, if we have a greater than 1,500 square foot home, we need a 50% capture efficiency. That means that we're capturing 50% of the pollutants off of that, through that hood, off of that electric range, or 110 CFM. Now, if we have less, if we're going from 1,000 to 1,500, that capture efficiency is the same. But notice if we have gas in both of these, we have to have a 70% capture efficiency or 180 CFM. And if we're looking at 1,000 to 1,500 square feet, an 80% capture efficiency or 250 CFM. And 750, if the home gets smaller, notice the capture efficiency goes up over electric. The CFM goes up. Notice the capture efficiency goes to 85 to 280. And so Bottom line is, if we have a really small apartment, you're looking at a minimum capture efficiency of 85% or a 280 CFM fan. So this was all really originated out of some work that Lawrence Berkeley National Labs did. And this was to try to control those PM 2.5s. So to encapsulate or to get rid of the PM 2.5, you're looking at minimum capture efficiencies of 50 to 65% or 110 to 100, roughly 60 CFM. And then the NO2, again, same numbers. The California standards are based off of this. 80 to 85% capture efficiency and 280 CFM. So what I did in my home, I just simply switched out my gas range to induction cooking. Induction cooking gives you the control of gas without the extra, pollutants and the concerns over that. And the beauty of induction cooking, it heats the pan, not the surface. So it's much more efficient. Here's a good example of that, where you can see that the egg is cooking, where we have the induction, ready pan, so to speak. When you're looking at the efficiency of induction cooking, according to Department of Energy and Energy Star, the per unit efficiency of induction cooking tops is about 5 to 10% more efficient than conventional electric, and about 3 times more efficient than gas. And if all cooktops when sold in the U.S. in 2021 use induction technology and meet the appropriate drafting criteria, the energy savings would exceed about $125 million a year and 1,000 gigawatt hours of energy. EPRI did a study. Induction cooking is considered one of the most efficient types of technologies, with up to 90% of the energy consumed being transferred to the food. So again, it uses the electromagnetic energy to excite the energy of the molecules in the pan, as opposed to transferring the heat from an element to the pan and then into the food. So it's quite a bit more efficient, 70% versus 40% for gas. Questions?
I don't see any in the queue at the moment, Steve. So I would say go ahead and carry on, and we'll get to some if they come through later.
Sure, okay. And we'll finish up here with heat pump clothes dryers. We're just about done. It's always been kind of interesting to me when you look at clothes dryers, they draw anywhere between 110 and probably 180 cubic feet of air per minute out of your house. So it takes heat out of your house. Let's say in the winter months, you heat the air to heat that air, and then you're going to take that air and reheat it to dry your clothes, and then you're going to push it to the outdoors. In the summer months, you're taking air that you've air conditioned, you're pulling that into the dryer, you're heating it up, and to extract the heat out of your clothes. So it's incredibly wasteful. So the concept of a heat pump clothes dryer is that it uses the heat pump to basically evaporate the moisture from the clothes. So you end up getting about a 50% energy savings. They're ventless, so you don't have to have a flue like or don't have to have a exhaust to the outdoors, not a flue. They're also, since they're lower temperature, they tend to be easier on fabrics, but they do take longer. Now the unit I'm going to put in is going to be, it's a hybrid system, so it has a little bit of an electric element in it if I want to use it, if I need to get stuff dried quicker, but it also has the heat pump component. So a lot of the newer units are what we call hybrid dryers, where they have an electric element to give you boost. So when you don't have time, you can dry your clothes quicker. Because obviously there's slower drying times because it's taking the heat, out of the clothes using the refrigeration cycle. So it's pretty cool technology. There's, as I said, no vent, easier on fabrics, lower temperature drying, does not depressurize the home. Your typical dryer basically takes that 100, let's say 30 CFM of air and is sucking that out of your house. That can tend to be a little bit pricey, $1,300 to $1,800. They do require your condensate drain or some type of a tank, but guess what? You already have a drain there for your washer anyway, so that's typically not a problem. And they can be, slightly noisier. So those are some of the pros and cons. But essentially, this is kind of how it works, is that you have this miniature little refrigeration cycle in here where you have an evaporator and a condenser, and you basically take this blower, and it's got double filtration on it, by the way, so it's really important that you keep the filters clean on these, because the efficiency of this system is going to be dramatically impacted if the filters are dirty. But essentially it extracts the water from the air, which is basically from your clothes being wet, and then recovers that energy and then delivers that heat into the drum. So it's a pretty simple process. So I've had extremely good luck with my heat pump water heater, so I'm hoping that this provides me the same level of performance. So wow, we've covered a lot of material in a short period of time. I know I tend to move fast, particularly in light when we have lots of questions, that tends to slow things down a little bit, but I always like to answer those questions. And so I'm happy to take some time now to answer some questions, and if I've been unclear about some things, please speak up.
All right, as Steve said, this is the last call for questions. We do very much appreciate you sticking with us and checking out all the information that he had, because there is a lot to cover on this topic. Just kind of answer a general question that some people might have, and that is that a video of this entire session is going to be posted online. Green Building Media will send out a link to that later this week. So in case you missed any part of it, or you want to replay it to your heart's content, go for it. We did have one question from Daniel. Will all electric homes be more greatly affected by utility programs that control peak load periods?
Yeah, what's happening, particularly in the West, and it's happening more and more everywhere as more and more solar and more renewables come online. It's shifting the peak load to the evening hours of the day. So once the solar sort of shuts down, starts shutting down, these utilities have to ramp up these power plants in a very short period of time. And a lot of the utilities don't have what they call peaking, or don't have as much peaking power plants as the load would require. So many of the states are starting to have their energy codes reflect the fact that when you use energy is just as important as how much energy that you use. So some of the utilities will handle this by having rate structures that are punitive to using energy during peak times. Other utilities will provide load controllers to customers as an option. So they control when your air conditioner runs on and off. They'll cycle, air conditioning on and off. Like for example, the Rheem water heater that I showed you, it actually has a module that you can plug into it where the utility will give you a lower utility rate if you allow them to control when your hot water heater runs and not. So the utilities have two approaches to controlling these peak loads. One is by rate incentives, which means that if you use electricity during those peak times, you'll pay more. Like I mentioned, Arizona, maybe as much as 30 cents a kilowatt hour. California's almost all the major utilities are 50 cents a kilowatt hour, or they'll encourage you and financially incentivize you to use load controllers. So yeah, it's as we start to move more towards an electrified society, it's not as simple as it looks, because the grid's got to be able to handle all this, and some cases the grid's capable of it, in some cases it's not. So it's going to be it's going to be a process, and that's why what this webinar was really all about, is trying to say, hey, if you want to help move this process of electrification, you can switch to these appliances, but let's just do it in an efficient, smart kind of way, where we're not just looking at simply replacing equipment, we're looking at the entire home so that we can be more effective.
Well, you mentioned the grid, Steve, and Daniel kind of had a question about that. He wanted to know what are the most cost-effective grid improvements that can be made at the local level?
Well, that's really about utility planning. I mean, and some utilities are much better prepared for this than others based on, just, how they're set up. But I can tell you, in my personal situation, when I went to switch, my code required me to upgrade to a 400 amp service, even though my home is going to be 4 times more efficient. But so part of it's the codes are outdated. But having said that, when they looked at my panel, my electrical, my transformer, they said, wow, we don't know if this transformer can handle this. Sure enough, come back, they said they could. But then I thought, what happens when my other 3 neighbors want to upgrade? So really, it's on a very localized level. And that's why I said that if electrification is going to happen, it has to happen on the customer side of the meter first, because we need to make our homes as energy efficient as possible. So we put as little load on the grid as possible so that, we can all get there in a more timely way, if that makes any sense.
Question from Daniel, or I'm sorry, not Daniel. We already got his Daniel's question, but to Lad's question. What are the options if you don't have a range hood that is vented to the outside and all you have is that kind of under cabinet microwave unit for a fan? And I can relate to what his question is because that's what's in my kitchen.
Well, in my 1970s house, that's exactly what I have that I'm living in now. Why I'm building the other house, I have the same exact thing. I have a microwave that is not ducted to the outdoors. Now, fortunately, it's house all electric, so that's not, and it's not a coil type burner. But yeah, I can't emphasize enough about the importance of having a ducted ventilation system to the outdoors. So unfortunately, if you have a gas range and you have a microwave that's not ducted to the outside, about the best you can do is use that filter and keep that clean and to at least keep some of the impurities, but it's unfortunately ducted to the outside is what new codes require. And in older homes, it's really a little problematic. So if you have an older home and you switch to induction range, that would certainly help a lot. But whether you have gas or electric, I really believe that ducted to the outdoors is, obviously the best way to go. I know that's not the magic answer you want to hear, but unfortunately, that's the case.
Well, Michael had a question about going back to ground source heat pumps. Wanted to know if you could talk a little about that, and are they as advanced as the current air source variable rate fan systems are?
I thought I had some slides in there on that. My other heat pump class, I have a lot of slides on water source and ground source heat pumps. So to answer your question, they are more efficient. And the reason is because if you go down deep enough into the ground, the water table is going to be go down deep enough and you hit the water table, that water temperature is going to be the average outdoor temperature for the year. So instead of it being, 5 below zero, it's going to be in the 50s, for example. If it's a ground source heat pump and you're down below the frost line, you're probably looking at temperatures that are substantially warmer than the outdoor air temperature. So the most efficient these systems is the first day of the heating season, and the least efficient is the last day of the heating season. Likewise, the most efficient they are for cooling is the first day of the cooling season, and then the least efficient is the last day of the cooling season, because you have all that thermal mass that stored that heat. So the beauty of these metrics that the DOE provides, it allows you to use that to judge the efficiency of the system that you have. So traditionally, when you're looking at ground source or water source heat pumps, you're going to typically be looking at the COPs, or the heating seasonal performance factors. And again, they buy the highest you can afford. So to answer your question, are they as sophisticated as the cold climate heat pumps? No, but they kind of don't need to be, because air is not the medium that you're transferring the heat. It's either the ground or the water table. And what I mean by the water table, what I mean by ground loop, they basically take and circulate that ground water over a coil. It's not like you're just pumping water out of the ground and pouring it over a coil and then dumping it into a lake or a stream. Did I answer that question? Okay, can you still hear me, Mike?
Sorry, I had myself on mute.
Scare me there for a minute.
Yep, I was trying to sing again. That's what it was. No, I don't have any other questions right now, Steve. So I want to go ahead and call it there. But I do want to thank you very much for sharing your time today and all the information that you did share with us, because this is a huge topic and there's different facets to it. And I love how you were able to kind of touch on all of them, or at least most of them.
You're welcome. Happy to be here.
All right. Thank you also to our wonderful audience for attending and asking wonderful questions. We love doing this for you all. And thank you also to PowerShift by NV Energy for their generous sponsorship of this webinar. Now, our next webinar is actually going to take place in 5 weeks. That's going to be on Wednesday, March 15th at 2 p.m. Eastern Time. We'll be talking with Stephanie Coleman about ESG in housing and what we can learn from the largest builders. So stay tuned to your inbox for more information from Green Builder Media on that one. Until next time, stay safe, stay healthy, and take care, everyone. So long.